Oh, we got, today we're gonna finish up getting all the data collection. Yes, this lab is due tomorrow, okay? So, here's what we got on Friday. And there's two very important words in this problem. And that's the fact that you are pulling that block at a constant velocity, which means all the forces add up to equal to 0. They don't add up to anything weird. They don't add up to pi or -4, okay? They just have to add up to equal to 0. So what you measure, like let's say for example, there was that wood-on-wood kinetic friction. Because remember, kinetic friction means in motion. So let's say that took you 1.20 newtons of force to pull it. Now, there's a couple of things that are important about that number. First and foremost, understand this. The only reason that you had to keep applying that force to keep that block moving was because there was friction. So one of the conceptual big ideas that you have to get out of your mind is the idea that a force is always needed for friction. That's a very old school Aristotle view of the world, okay? The new view is that, hey, you eliminate that friction, you don't have to keep applying the force. And this is this concept of inertia, where an object wants to maintain a constant state of motion. So what that 1.2 newtons is telling you is basically we're saying that's how much you have to pay the frictional mafia. So the frictional mafia is -1.20 newtons. So whenever you figure out how much force it takes to pull something at a constant velocity, that's the value of the frictional force in the opposite direction, okay? Now, let's also get rid of another misconception. This is not Newton's third law that says for every action there is an equal and opposite reaction. This is not Newton's third law. Newton's third law occurs where you have that hook and then you have the Newton scale when you're pulling it. That's Newton's third law. That's where, oh, you're pulling on the block is pulling back on you. The force friction and the force applied are not Newton's third law. You can have Newton's third law when you say, oh, gravity is pulling down on the table is pushing back on the block. That would be Newton's third law, okay? Newton's third law is not, oh, the applied is balancing out the force friction. That third law is referring to, hey, what happens in a situation where you have one force and then you have that force acting in the opposite direction. You push on the door pushes back on you, okay? That would be Newton's third law. Okay, so diagram number 1. This is what diagram number 1 should look like. It should look like a big plus sign. Show me the scale. Hey, what did you let 2 centimeters equal Newton? Did you let 3 centimeters equal Newton? Show me the scale. Label the values. Force applied, force friction, gravitational force, and force normal. Okay? And they're all emanating from either like the edges of the block or the middle of the block. I don't care. Some people like to draw them, like they'll sketch out a little block, and then they'll draw the forces going from the edges of the block. Some people like to put just one dot in the center and then draw all the forces acting from that dot. I don't care. Pick one, okay? Just pick one. So that's diagram number 1. But you're only drawing one of those, and you're only drawing it for the wood and wood surface at a constant velocity. Okay, that's the only one you have to draw. The next one is that you're going to draw these tip to tail. I always put my gravitational force first, then my force applied, then my force normal, then your force friction. Okay, use the same scale that you used on the first one. Don't change the scale. Okay, use the exact same scale. All you're doing is instead of drawing them from a free body diagram, you're drawing them tip to tail. Now, every tip to tail system of forces can only end up one of 2 ways. Only one of 2 ways. You either end up back at the origin and you have a constant velocity, or you don't end up at the origin and you accelerate. That's it. Those are your only 2 options. So as soon as you see the word accelerate, like when you get down to number 7 and number 8, which we'll talk about in just a second, as soon as you see the words accelerate, you know the forces do not add up to equal to 0. And every time it accelerates, you only have one of two options. You either speed up or you slow down. That's it. There is no other option. So every force problem, I'm telling you, every force problem can only do one of three things. Constant velocity, you speed up, you slow down. That's it. That's it. There's nothing else. All right. When you get down to the next part where you stack weights on top of the block. So remember, there's two ways you can determine the weight of an object. One, like for example, you guys took a 200 gram mass. So if you know what that is, you can take 0.2 kilograms times 9.8 meters per second squared, and you're going to get 1.96 newtons. So one way to find the weight of an object, take the mass, multiply it by g. Okay? Don't worry about making it negative, just get the number. Okay? Just get the number. Then you want to add that to the weight of the block. So Caitlin, like, what did your guys' block weigh?
For 200?
No. Just the block itself.
Oh, 3.95 newtons.
3 point what?
95 newtons.
Okay, so you guys are going to take 3.95 plus 1.96, 5.91. So the total, your total F normal is going to be the total weight of the block, which in your guys' case would be 5.91 newtons. Okay? Because it's the 1.96 newtons, the 200 gram mass, plus the weight of the block. Because that's the total amount of downward force that's being exerted. Then, you're going to measure how much force it takes to pull it at a constant velocity. So like, how much force did it take you guys?
1.5 newtons.
Okay, exactly 1.5?
1.5. Yeah, 0.
Okay, 1.50 newtons. You have to be consistent on how you record the data from those Newton scales, because these Newton scales read out to the tenths and the hundredths place. So don't record that as 1.5, because if you record that as 1.5 and not 1.50, it looks like you're using a different measuring device than what you use on the other stuff. Okay, so if it's exactly 1.5, write that down as 1.50. All right, so then what you're going to do, here's graph number 3. So you're going to put on this graph the force normal on the x-axis, boom. And then you can have your force friction, and you're going, but Mr. Burkham, we don't know what the force friction is. Yes, you do, because you know how much applied force it took to pull it. So by measuring the applied force, you have, in effect, measured the frictional force. Okay? So if it takes you 3 newtons to pull it, that's because there was a frictional force of negative 3 newtons. So you're going to plot these points, okay? And then you're going to draw a line of best fit. It might start at 0, 0. It might not. It depends on, you just have to look at what your data gives you, okay? So here's what's important. You're going to come in here and you're going to circle the points, and you're going to write those values down that you're going to use to find the slope of best fit. Now, look at what you're doing. You're on the y-axis, you're putting force friction. On the x-axis, you're putting force normal. So what if you get if you take force friction and divide it by force normal?
Mu.
Yeah, you're finding the coefficient of friction, because you're finding mu, because you're graphing the slope, which is force friction over force normal. Okay? So by finding the slope, you're finding the coefficient of friction, because that's what you're dividing out. Okay? Makes sense. Cool with that. Now, when you get to question number 7, so let's talk about this. So here's this car, boom, and you're moving at 10 meters per second. So the little arrow I have off to the right over here, all that's telling you is that, hey, this is the direction that the car is moving that looks like a box. So you're gonna apply the brakes, mu is 0.7, what's the value of the frictional force acting on the car? And you know that the mass of the car. Now, notice that is the mass of the car. It isn't the weight of the car, it isn't the normal force, that's just the mass. That's all that is. But, Gavin, every time you have the mass, what's one thing you can find if you know the mass and you know what planet you're on?
Force.
There's a whole bunch of them. You gotta get more specific than that.
Force normal.
Nope.
Force gravity.
But then you can use that to find the normal force.
Yes.
Okay? Because remember, Fg is just mg. Oh, take 1,000 kilograms times 9.8 meters per second squared. Boom. There's your gravitational force. Now, by knowing the gravitational force, what else do you know?
Force normal.
Then you know the force normal. Okay? Cool. Now, think about this. Here's this car moving along. Okay? So here's this car moving along. You hit the brakes. Is the car going to accelerate when you hit the brakes?
Yes.
No. Yes.
That's the whole point of hitting the brakes. If your car doesn't accelerate when you hit the brakes, you have problems. Okay? So, but that acceleration is going to make it do what? Speed up or slow down?
Slow down.
Slow down. So basically what you're saying is that you want to take your velocity time graph and give it a certain slope, okay? You want to go from 10 meters per second to 0 in a certain amount of time. You are going to make it accelerate, okay? That's the whole point of this story. You're going to make it accelerate. Now, you know that mu, which is what you all just found, is force friction over force normal, okay? I gave you mu, that's 0.7. You can find your force normal. Oh, cool. Because force normal was the same as your weight, so then you can find your force friction. Now, these are all absolute values. So mathematically out of this, you're going to get a numeric value of a force friction that's a positive value. What you have to decide then, in the context of the problem, do you make force friction positive? Do you make force friction negative? Now think about this. You have a positive velocity for the car. What sign do you think the acceleration is going to have? Negative, because you're slowing down, right? Well, the only way you can have a negative acceleration is if you have a negative force, okay? So you can find your force friction. It's a positive number. And then decide, hey, do I make this positive? Do I keep it positive? Or do I change it into a negative, depending upon the context of the problem? Now, let's say this is the velocity time graph slope on dry pavement, okay? Now, let's say we get into the winter, we have a bad ice storm. You're driving along at 10 meters per second, but the roads are icy. What's going to happen to the slope of that line when you hit the brakes? Is it going to be more steep or less steep?
Less steep.
Less steep, okay? Because it's going to take you longer to stop. So your ice line might go out like this. Now, this is a logic situation. Okay, cool. What does the slope of a velocity time graph give you?
Acceleration.
Acceleration. In which situation do you have a steeper or bigger acceleration? The dry line or the ice line?
The trial.
Dry line. Steeper line, bigger acceleration. Ice line has a smaller acceleration. Well, if you have a smaller acceleration, why do you have a smaller acceleration? Because you have a smaller force, because ice doesn't have as much frictional force as dry pavement does. So this is why when it's icy and snowy, always leave a lot of space between you and the cars around you, because your coefficient of friction is going to be a smaller value because you're not gonna have as much force friction. Therefore, your velocity time graph is more shallow. And now here's the last thing. What does the area underneath the velocity time graph give you? Displacement. Oh, if it's icy, you have a greater area underneath your velocity time graph, therefore it takes you longer to stop, both in terms of time and distance that it takes for you to come to a stop. Okay. When you get to question number 9, question number 8. So a car with a mass of 950 kilograms, moving 15 meters per second, is brought to rest in 220 meters. Determine the acceleration of the car, frictional force, and mu. Okay? So here's what I want you to see. At the beginning of the lab, how did you all find the force friction? What did you do?
We pulled it into.
And you measured the force
Yeah.
applied, which is balancing out the force friction. On problem number 7, how did you find the force friction?
We had the frictional constant, and the force normal.
You have the coefficient of friction, and you have your,
Force
Force
normal.
normal.
so you know that mu times force normal equals force friction. Okay, that's the second way you can find your force. Pull it, use mu times force normal. Now, so here's this car. You hit the brakes. You got your gravitational force, you got your normal force, and you have some force friction. Okay? Is that force friction going to create an acceleration? Gavin?
Yes.
Stretching, bro. I didn't see
That's
it.
not what I asked.
So,
Is the force friction going to create an acceleration?
yes.
It better. If it doesn't, you're going to crash.
Yeah.
Very funny
Is force friction a force, Gavin?
Force friction is in fact a force.
Could you, then does that equal mass times acceleration?
No. Yes.
Buddy.
That's for force gravity.
Any force can be written as mass times acceleration.
Oh, okay.
Okay? So, on problem number 8,
You didn't know that. Stop laughing.
any force can be written in terms of mass and the acceleration that it causes. So, on number 8, what do you know? This is what you have to do acceleration problems before you do force problems. On number 8, what do you know? What values do you know?
Force friction.
No, you don't.
You know the
Acceleration.
mass.
You know the mass.
velocity.
You know which velocity, the initial or the final.
The distance.
Initial velocity.
You know the
And
initial
the final
velocity, you know the final velocity is going to be,
0.
Zero.
you know distance. What do you not know?
Acceleration.
And you don't know which variable also do you not know.
Time.
So what are you going to do? What are you going to use if you don't know time?
That equation.
So on number 8, you're going to use that equation to find the acceleration. Once you know the acceleration, then you can use F equals ma. And then once you know the force friction, then you can go, oh, mu equals force friction over force normal. Now, how are you going to find the normal force? You know the mass, so what can you find?
Find force gravity.
And then force gravity is opposite of your
Force normal.
force normal. When you find mu on number 8, is that going to be a positive or negative number?
Positive.
Because it's an absolute value. Okay? All right. Number 2, this is the equilibrium one. This is the one that I set up. This is where you're going to have the table. And you're going to have 3 forces acting on the table. A is going to be the one that's 0 degrees. That is the one you are forbidden from changing. Okay? And you can change the mass on it, but you can't change the angle. So A is going to be 0 degrees. You're going to measure around counterclockwise. So B might be like 120 degrees and C might be, I don't know, 255 degrees, whatever that is. So A is at 0, counterclockwise, just like you've done before. So the mass column, that's going to be in kilograms, whatever, how much ever mass is on the end of the string. And then your FG is going to be just the weight of what's ever pulling that down. So here's the basic idea, is that this is a three-way tug of war. So there's A, there's B, there's C. So this is like just the free body diagram sketch. So what you need to do to generate the fourth diagram, down there on step 3 where it says determine the scale from the vectors and add them tip to tail, label your vectors. So what you're going to do here is, again, this is to scale with a protractor. You're going to draw vector A, from the end of that you're going to draw vector B, from the end of that you're going to draw vector C. In an ideal world, you should end up back at the origin, okay? Or pretty close. You might not end up exactly, but you should be pretty close. If you end up out here, something has gone horribly wrong, okay? Then you're going to use that to answer those questions. Now, what I want you to visualize when you answer question number 6, if the string of vector B had been cut, in which direction would the ring accelerate? Give a specific angle for the acceleration. So imagine this. We're going to cut that string. Now, think through this. This is a three-way tug of war, okay? A is balancing out the resultant of B and C. C is balancing out the resultant of the other two. So each vector is balancing out the resultant of the other two, okay? That's it. It only works. Three-way tug of war. Everybody is working on their own to balance out the effect of the other two, okay? So imagine that if you could take, there's vector A, there's vector C, and then you could draw that resultant. So visualize this. You don't have to calculate it, but if you visualize it, you'll know exactly what you have going on. Okay, bring your lab with you. Let's go to the back, and we need to talk about the next part. So stop that, bring that. Okay, so here's the third and final part of the lab. You're going to have a track like this. You're going to have a 500 gram mass. Then you're going to have a cart. String attached to it, goes over the end, got to pull it. So, what we're going to do is we're going to look at the effects of applied force on a system. So here's the story. Just focus on this for now. Don't worry about the rest of the system. How can you figure out how much a 10 gram mass weighs?
10 times 9.8.
Not 10. Not 10. It's 10 grams.
Oh, 2 grams. So it's 10.
0.1. Or
0.01.
Would you divide by 1,000?
Yeah.
So do this. Take your calculator. Elliot, take 10 divided by 1,000, because y'all are horrible at mental math,
That's right.
and then multiply that by 9.8.
0.098.
0.098. Okay, so this weighs 0.098 newtons. Okay, it's what it weighs. Now, here's what I want you to see is the difference. If I just drop it, how much force is acting on this mass if I just drop it? Do not make this difficult.
9.9.
Negative 9.
Negative.
Oh,
Negative
negative
0.09.
in newtons.
Don't worry about the negative sign.
The newtons.
Well, and what was the number that we just...
0.09.
Oh.
0.098.
Yeah.
Okay, do not make this difficult. Okay, if I just drop it, what's the only force acting on it?
Gravity.
Gravity, which has a value of
0.09.
0.098.
Bien.
Now,
You're maxed
Gavin,
out for the day.
just
It's 2.
put the stuff down.
Yeah.
Stop. Stop.
Just
Bert, I have a question. Is this the block that Aiden Turner broke and had to reglue?
I don't remember. It could be. Okay. Now,
Yep.
I let go of this. The only force acting on it is 0.098 newtons.
What's that?
So if you know that this is 0.098 newtons, and you know it has a mass of 0.01 kilograms, could you determine the acceleration?
Yes.
Yes.
Yeah, you would take 0.098 newtons, divided by the mass, and oddly enough, you would get an acceleration of
0.98. Negative 9.8.
There we go.
9.8, okay? Because
Yeah.
that's the acceleration, right?
Yes.
Okay. If I take a 20 gram mass, 20 gram mass, it has more stuff, it has more inertia, right?
C.
Elliot, take 20 grams, divide that by 1,000,
Is it 0.196?
0.196. So this weighs 0.098 newtons. This weighs 0.196 newtons. Do they weigh the same?
No.
No, clearly not. This weighs twice as much because there's twice as much stuff. Now, this weighs twice as much. But when I drop it, now I'm going to take 0.196 newtons and divide that by the mass. What acceleration am I going to get?
9.8.
Ah! So do they have the same force acting on them?
Yes.
No!
No. That's a.
This has a force of 0.098. I'm talking the value of the force.
Oh,
Okay.
okay. Never mind. No,
Same type
they
of
don't.
force, but
This has 0.098 newtons. This has a force of
0.196.
0.196. But when I drop them,
Or I think you're backwards.
do they get the same acceleration?
Yep.
That's the whole point of the story. So the first thing I want to get out of your minds is that, oh, heavier objects fall faster. They don't. Okay? Is there more force acting on the bigger mass? Absolutely. But it also has more inertia. It has more stuff. It takes more force to get it to move. Okay. So in terms of data, here's what you're going to do. Take 500 gram mass, boom, stack that there. Take the 20 gram mass, put that up there. Now, what you're going to need over here is that you're going to need the mass of that cart. But you don't have a scale that measures mass. But you do have a Newton scale. So if you can hook it up and find out how much it weighs in newtons, how can you find the mass of the cart?
Well, you have,
Math.
Math.
you
Mass.
have acceleration and you have force. So you just, wasn't it?
Yeah. So let's say that this should weigh about 5 newtons. So if this weighs about 5 newtons, how can you find the mass of it? Divide by,
Acceleration.
Acceleration.
what's the acceleration due to gravity?
9.8.
Yeah, so take whatever this thing weighs, divide it by 9.8 newtons, and that's going to be your mass. You're also going to have a 20 gram mass. You're also going to have a 500 gram mass. You're also going to have a 10 gram mass. So at some point, you're going to need the total mass of the system. You're going to take 10 plus 20 plus 500 plus the mass of the cart itself. Now, in terms of data, here's what you're going to do. You're going to take this tiny little 10 gram mass, which weighs 0.098 newtons. Now hook it up. And you need this to have a displacement of 50 centimeters. Okay? I don't care really how you set it up. So I'm going to move this back to like 30. And then I'm going to make that thing move till it gets to 80. Okay? I don't care which points you pick, you need 50 centimeters. And later on you'll see mathematically why that's handy. Now, I'm going to let go of this. The only force acting on this is this 0.098 newtons. That's it. But will it accelerate at 9.8 meters per second squared?
No.
No.
But the only force acting on it is 0.098
Oh, then
newtons.
yes, that will.
Oh,
Really?
friction.
No. These are frictionless
Oh,
traps.
yeah, fair. But then also, that's
That's
pulling
weighted.
itself down.
That's mass,
How
okay?
is it frictionless?
Because the wheels are pretty much frictionless, that's why. It
Your-
isn't exactly,
your main
but we're
tool
going to
here.
assume that it is.
Okay.
So here's what you want to look at. Is gravity pulling down on this part up here?
Yes.
But what's there to balance it out?
Force.
The track.
The track. Gravity is pulling down on this, but the track is going, whoa, whoa, I got you. Gravity is pulling down on here, okay? Still 0.098 newtons. But clearly, there has to be an upward force to prevent it from falling at 9.8 meters per second squared. So the string is providing an upward tension force. So there's an upward tension force. There's still gravity pulling it down. Now, which one is bigger? The gravitational force pulling down or the upward force of tension?
Tensional.
Because if the tension force was bigger, what would it do?
It would go the opposite way.
Well, it wouldn't move or it would move up. Okay? So by virtue of the fact that it accelerates in this direction, I know my downward force has to be bigger than the tension. So here's what you're going to do. In terms of data, you're going to have trial one. What you're going to do is you're going to record the time it takes for this to happen. Get your phones. Shh, don't think. So you're going to start at that leading edge, whatever point it is. I'm going to call it 0.3. And then that's going to move down to 80. When it crosses that, that's when you stop the stopwatch. Don't stop it here, okay? You want it moving while it still crosses it, because otherwise you're including the stop in your time. So stop the stopwatch when it crosses that mark, but stop this later on. So you just want to make sure that when this thing travels the 50 centimeters, that it's not hitting the ground before it hits the 50 centimeter mark. Okay? Cool with that?
Does it
See-
matter if we use the front or the back, or as long
Doesn't
as
matter.
it's consistent?
Doesn't matter. Just make sure it goes 50 centimeters. Okay. Now, so this is actually on one of the shirts, because I asked the kids when I was doing this one time, I said, why does it happen? And there's actually some truth to it. Because it has room to fall. Okay? So if I put this up here, nothing happens. Doesn't have room to fall. You put it over here, and it does have room to fall. Now, here's what you have to understand to calculate your acceleration. On this column right here where it says force net, that force net is going to be whatever the weight of the hanging mass is, which for you guys on that first trial was going to be 0.098 newtons. Okay? That's it. Because that's the only force available to accelerate the system is that 0.098 newtons. Force equals mass times acceleration. We just don't divide by the 10-gram mass on the end. We divide by the 10-gram mass, the 20-gram mass, the 500 grams, and the mass of the cart. So this is kind of like you're going out on a date. Gravity is pulling this thing down. But as you're going out the door on your date, mom and dad yell, hey, you need to take along your little brother Timmy on the date with you, okay? So this is like dragging Timmy along on the date. What's going to happen to your acceleration? It's going to be much slower because you got to bring Timmy, okay? You're going, wow, I got this date, it's going to be cool, and then mom and dad go, you got to take Timmy, okay? Bummer. So you're going to do 5 trials. You're going to take the average time. I would have at least 2 people timing this. Compare your times. So when you get done with those 5 trials, then you take the 10-gram mass off, put that back up here. And then you're going to take the 20-gram mass and put this on the end. What have I done to the total mass of the system?
I did the same, right?
Total mass is the same. What have I changed?
Where it goes.
Yeah. So now I've got a 20-gram mass on the end. What does a 20-gram mass weigh?
0.196.
0.196 newtons. What have I done to the force acting on the system?
None. Well, you did nothing to gravity.
Doubled it.
I doubled it.
Oh.
Because I went from a 10-gram mass to a 20-gram mass. Do I still have the exact same mass in the system?
Yes.
Yes. So if the same mass is on the system and I've doubled the amount of force, what should happen to my acceleration?
Stays the same. Doubled.
It should double, because I have twice the force acting on the same mass. So now when I let go of this, you notice that that acceleration is noticeably bigger than when I had the 10-gram mass. But this is why we took that 10-gram mass and put that back up there. Now, we're gonna do a whole bunch of different problems like this. I'm gonna preach this again and again and again and again and again. You always divide by the total mass of the system, okay? It's always the combined mass. It's never the mass on the end, it's never the mass up here on the cart. It's always the total combined mass of the system. So, what you're going to end up with is that you're going to have these trials, 5 trials with the 10 gram. Swap it out, put on the 20 gram, boom, there you go. That's what you've got. So, got the idea of what's going to happen. Stop the camera, let's go back up there. We'll do a little wrap up and then I'll come to it. Okay, are we going? Thank you. All right. So here's going to be this last setup. You got a 10 gram mass hanging from the end of the string. You got a 500 gram mass, 20 gram mass, and the mass of the cart itself. When you find the weight of that cart, that should be about 10 newtons. Okay, so those carts typically weigh around 10 newtons. Okay? So, excuse me, I'm sorry, they should weigh around 4.9 newtons, around 5 newtons. Okay? If you don't get that number, probably what's happening is that the frame of the cart is catching on like the scale itself. So when you hang that up, make sure that you are only holding up the weight of the cart. So you're going to measure the weight of the cart, determine the mass. Boom, 4.9 divided by that, you should get around 0.5 kilograms. So the cart is around 0.5 kilograms. You're going to have a 500 gram mass, and then you're going to have a 10 gram mass and a 20 gram mass. Divide that out, add all those numbers together. Keep a lot of significant digits. So, on the 10 gram mass, down there where it says net force, on that 10 gram trial, that net force is going to be the weight of what's ever hanging from the end of the string. Because what we're assuming is that there's no friction in the opposite direction, okay? Now, do not confuse mass as an opposing force. Does this resist motion? Absolutely, okay, it does. But dragging that mass is not an opposing force. How we take that into account is that we know that force net equals mass times acceleration. So when we divide that net force by a big mass, that's how we take that into account. If there was an opposing force, there would be something like friction. Okay, I would have to tell you, hey, the frictional mafia is pushing with a certain amount of force in the opposite direction. Or we put a fan on it, and the fan is providing a certain amount of force in the opposite direction. Okay? So that's why I said you just assume that this is a friction on the surface. So whatever the weight of whatever hanging down, which in this case is 0.098 newtons, you divide that by the sum total of the mass, there's your theoretical acceleration. Now, you also need to calculate your experimental acceleration. So, if you look at what you know that it traveled 0.5 meters, so you know a distance. What else do you know? What did you measure? Time. You're going to know the time. Okay? What else do you know? You know one other important thing.
Initial velocity.
Yeah, you're clever. You let the initial velocity be 0. So what old school kinematic equation relates distance, acceleration, time, and initial velocity?
Something like
The
v initial t or something. Oh yeah, x equals v initial t, and then 1/2 acceleration t squared.
Okay? Now, you're clever. What'd you let the initial velocity equal?
0.
0. Oh, okay, cool. It could have been moving, but would have been a lot of work. Okay, so you let the initial velocity be 0. So you need to get acceleration by itself. So what are you going to do? Oh, 2x divided by, this is why we let the distance be 0.5 meter. because then you're just taking 2 times a half a meter, otherwise known as 1. So you're just taking the inverse of time squared. Okay, that's why we let it be that. So, your theoretical acceleration, you're going to use force net equals mass times acceleration. That's how you're going to get your theoretical acceleration. Your experimental acceleration is going to be 2x over t squared. That's how you're going to get that number. Okay? So, that's all the data that you need. Then you have a lot of questions to answer. Okay? I'm just saying. And by the way, when you get to question number 10, I give you 3 statements, and you have to explain why they are false. Okay? That last one, your gravity is negative 9.8 meters per second squared. Don't sit there and go, oh, that's false because it could be a positive value. That is not what makes that statement false. Do not get hung up on the signs. Look at the trend in your data. Okay, I'm done. Get the force table data, get the other data, then you have much to do. And this is due tomorrow. So, you're on your own.
The end.